So what is classical physics? What does it explain, and what are its limitations? So if I look around me in this room, I see a bunch of objects. Each one of them has different color, maybe different smell, and it has a position. They're ordered in the room, and each one has a shape. So out of these properties, the shape, the color, and the position, classical physics or classical mechanics, or more specifically Newton's laws, explains the shape of things and how they're ordered. So for everything around you, you can explain basically their shape and where they are, but you can't really explain their color and their smell with just classical mechanics, because you need to go down to the atomic scale to explain things like light and smell, because those things involve molecules and things like that. Of course, you could imagine that going down to smaller and smaller scales would also be fine, because everything is just motion. You know, light, when it hits your eyes, is just kind of something moving, like a particle, a photon hitting your eyes. Or smell is basically molecules coming and like touching your nose. But if you want to go down to the atomic scale, down at those scales, at the molecular scales, we found that there's a theory called quantum mechanics, which replaces classical mechanics, which I will tell you about, and is more accurate down at those scales. Actually, also, if you're trying to move at speeds like close to the speed of light, you also find that there's another theory called Einstein's theory of special relativity and general relativity that replaces the Newton's laws that we will talk about. Apart from that, everything in the room, everything in the macroscopic world, everything that we see can basically be described by these laws. It includes everything from the atmosphere to the water of the ocean. What happens if the sun shines on the atmosphere? Like what kind of water flows result from that? What happens if this part of the ocean has more salt than that part? How will it move? How does global warming affect what the atmosphere looks like, and what kind of motions that happen? What happens like if the sun shines suddenly on the top of the atmosphere? That will cause forces. So a lot of things can be explained just by these simple laws that we will talk about right now. Okay, so what is motion? The motion is the description of moving objects. So you have a position, and the position is changing. So in order to define motion or understand it, we need to understand what is position, and we need to understand what is time, because it's moving through time. Okay? So let's start with position. So this theory, Newton's theory, describes the world of a point particle. Of course, there could be particles interacting with this particle, but we're going to focus on this single one. How do we describe this particle? We're ignoring the color and the smell of it and things like that, but we're interested in its position, right? So the position could be described by three numbers. You need to tell me where it's on this axis, so it's like left to right. How many steps do I need to move this direction? How many steps do I need to go up or down? And how many steps do I need to go side to side in order to get to the particle? So if this was my origin, I need to go a certain number of steps this way, and a certain number of steps this way, and a certain number of steps that way to get to the particle if it was here. And so in order to tell me where a particle is relative to this origin, you need three numbers, x, y, z. Okay? So this is where the theory lives in. Newton's theory lives in three dimensions. It's like you imagine that the space extends from here to infinity upwards, infinity downwards, infinity in that direction, that direction. So it extends in infinity in all directions. So you imagine a three-dimensional space. And that's where this point particle lives. Every point it could occupy is described by three numbers, right? And in order to describe its motion relative to this point, you need to understand how these points are changing with time. So you need a clock. So somehow there should be some object in the universe that is keeping the time. And you look at this object, maybe the clock is here, and maybe, so you start here, this point started there, and after some time this clock position is here and this point is there. So to get the speed, you just need to know how these three numbers changed. So you use the symbol delta, which tells you a change in a quantity. in some certain number of time steps, right? So that would give you the speed, or the velocity. The velocity of this particle is this much. This is how much it moves. It's in this direction, and you just have to divide this vector, which is also 3 numbers, right? You need to divide that by time, the amount of time that has passed. Alright, so this is where this theory lives in, but now we want to think about a philosophic issue. What happens to a point particle that is living by itself without anything else? Well, our intuition, or my intuition would say, like, how do I know whether I'm moving or not? I'm moving if there's air bumping into me, right? If there's no air bumping into me, then how do I tell whether I'm moving or not? And I can't see anything else, right? I'm in a dark room and I'm just sitting there. I don't feel anything, so I can't really know whether I'm moving or not, because there's no reference point for me to know whether I'm moving or not with respect to that point, right? This point looks the same as this point in empty space. But what actually Newton says is that even in empty space, there is something called absolute space and absolute time. And even in empty space, this particle cannot be changing its velocity with respect to this reference, with this coordinate system. So Newton's first law has to assume that, which I will just tell you what it is in a second, but it has to assume that there is an absolute space, absolute time. This particle compares its position to this absolute reference frame. So even in an empty space, a particle by itself, it can tell whether its speed is changing or staying the same. And so what the first law says, if there is nothing else, if there is no influence on the particle, that means absence of any forces, then the velocity doesn't change. What does it mean the velocity doesn't change? It means that if I'm moving this way, I keep moving that way. If I'm just standing still, I keep standing still. It doesn't mean that I always stop. So here's a question for you. Why, when you're driving and you remove your leg from the gas pedal, why doesn't the car just stop immediately? Because there's no force acting on it anymore. Why doesn't it stop immediately? Well, it doesn't stop immediately because of this law. Is that the natural state of the car is that it wants to keep moving by itself at the same speed that you were moving when you took off your foot. So it's moving at that state. If there's nothing else in the world at that time, if everything suddenly disappears except for the car, there's no other forces acting on it, it will keep moving at 100 miles an hour or whatever speed you had before you removed your leg, right? So the reason why it stops eventually is that there is something acting on it. The tire is interacting with the street and the street is slowing the tire down, and that's why the car slows down over time. But because of this law, the car doesn't stop immediately, right? So that's one question. Okay, so I have another question for you. You can pause to answer and then continue to see the answer that I will give you. So when you're driving in your car and you turn around, why do you feel like you're hitting the door? Why are you hitting the door? Why do you feel the force of the door? Alright, try to think about that for a second. Alright, so the reason is that it's again this. You want to keep moving at the same speed, you want to keep moving at the same direction. That's your natural state. That's your default state. If everything else disappears and you're still there, you will just keep moving straight. You're not going to be turning, right? So your natural state is to turn. So if your natural state is to go this way, but the car suddenly turns, you hit it. So you're hitting the door. You keep hitting the door a little by little, and the door is turning you. So the reason why you feel like you're pushed into the door when you're turning a sharp turn is because you want to keep moving just like you were moving, and the door wants to turn. So you basically keep hitting it, hitting it, hitting it. Every time you hit it, you bounce back. Like, you don't really sense these small events, but basically you're hitting the door, you're bouncing, you're hitting the door, you're bouncing, and then you're adjusting to it. So that's just looking at Newton's first law, which tells you what the default state of the world is, or the default state that this particle wants to have. It just wants to keep moving in the same direction that it was moving at the same speed. It doesn't want to change that. Okay? And the only way you can define or talk about this law is by having a reference frame, right? This particle, at least according to Newton's laws, this particle will not move unless something else acts on it. So it will not accelerate unless something else acts on it. So this is a subtle point. It has to do with Mach, who basically disputed this idea and said that it doesn't actually make sense for a particle to be moving when there's nothing else in space. It's a meaningless concept. The reason why we have particles, we sense accelerating, is that the rest of the world actually forms this reference frame for us. So if a particle is... so let me tell you the reason why Newton introduced this concept, why he said that, where he came up with this, where he came up with the idea that even in empty space you can't accelerate, that acceleration has a meaning. So if I get, again, let's use this as an example. So what he did is he rotated the bucket, right? And when you rotate this water, you can see that it's the water level is going up, right? So the cup of water knows that it's rotating, right? Even without anything else around it, it just can tell that it's going up. However, if you instead say, oh, the cup of water is not rotating, but the rest of the world is rotating around this cup of water, the water level will not actually rise according to these laws. So by that you can tell, even in empty space, even for a particle by itself, you can tell whether it's changing its speed or not. So Mach would say no, if you rotate the rest of the world around this water, then the water level will rise up. So that's the two kind of perspectives. Is there like a sort of an absolute reference frame, or is it only with respect to other objects? And this is a deep point. This is where Einstein got his special theory of relativity and general theory of relativity, which I might get to at some point. But it's a deep point. How does an object know whether it's moving or not? Am I sensing, is space by itself without any other particle, is that a real thing? Or is it only, am I only measuring myself relative to other things? I only know I'm moving if I'm feeling the air, but if there's no air, maybe it's a meaningless concept, right? So at this point, we'll leave it at that, and just know that whether it's there is an absolute reference frame, even in empty space, or the reference frame is defined by the rest of the universe, like the stars, the fixed stars and all of that. Whether those define the reference frame or not, we can leave that question for later, which is, we might get to that if we discuss general theory of relativity. But for now, practically, when we want to explain how this chalk moves, how other objects move, if you want to explain like the atmosphere, or if you want to explain the motion of water in the ocean, if we want to explain most of those things, we can do that just by following Newton's laws. Okay, so the other part, the second part of this law is Newton's second law, and it follows from, this law follows from Newton's second law. So that basically, you probably heard this before, so F equals ma. Right, this is the second law. So mass times acceleration. So that means if there is nothing else in the universe acting on my particle, then the acceleration, I will tell you what the mass is later, but if this is 0, then this has to be 0. right? So if the acceleration is 0, well, the acceleration is this change in the speed and change in the velocity. So if that's 0, then the velocity is not changing, right? So it's has the same value now as in 10 years later or 10 seconds later. So the value is not changing. That means it's moving in the same direction at the same speed. So if there's nothing else acting on it, then that happens. But now, I told you, I started this video by telling you that Newton's laws explain everything. They explain, or everything around us. They explain how this chalk moves if I let it go. It explains the vibration of trees, explains the motion of water, the atmosphere. It explains like how blood flows in your vessels, and explains many things. Okay? And that's only this. So basically, this equation is all there is to all those things, right? So what I'm trying to say is everything, all the complexity of the world is hidden in what the F is. At this point, I didn't tell you yet what it is. I just told you its definition. It's mass times acceleration. I didn't even tell you what the mass is. What we know so far is only the acceleration. We can define space. We can define where objects live. Like, you just need 3 numbers to tell me where they are, and how these numbers change in a second. That gives me the speed, and then how the speed changes in a second gives me the acceleration. So we know what this is, but what is mass, what is force, we don't know yet. And the hidden complexity of the world is basically hidden here. It's basically you have so many particles, each one has different masses, and they're all interacting in some way, and that generates tremendous complexity in the atmosphere, for example. So we'll talk about what this is and what this is later in a future video. In the next video I'm gonna talk more about how to define mass, how to get a number. We have an intuitive feeling of it. Mass is like how hard it is to change the state of something, but in order to get a number, you need to, we will talk about next time how, like, what does it mean for something to be 1 kilogram, right? Where does that number come from? Okay, so I hope you got something from this video, and see you next time.